Alright, so hello and welcome everyone to week 11 of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. The course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering of IIT Guwahati. My name is Debjit. I'm currently a PMRF scholar at IIT Madras, and like every other week, we shall be solving some tutorial problems together. So that brings us to the first question of today's session, which is asking us that for momentum conservation, the 2D steady convection diffusion equation is what? Is it option A linear? Is it option B non-linear? Or is it option C insufficient information? That is, with the given amount of information, it cannot be ascertained whether it's linear or non-linear. So it's a very simple question to begin with. Read the question carefully and try to figure out the correct solution. So for momentum conservation, the 2D steady convection diffusion equation is what? Is it linear? Is it non-linear? Or is there not sufficient information given in the question to determine whether it's linear or non-linear? So we'll quickly have a look at the solution. The solution is option B, non-linear. That's because the 2D steady state convection diffusion equation, which conserves momentum, becomes something like this. It becomes dou dou x of e, dou dou x of, let's say, rho u plus dou dou y of rho uv equal to minus dou p dou x. This I am writing for the x momentum equation. Dou p dou x plus mu into dou square u dou x square plus dou square u dou y square. Now, these two terms over here, the convection terms, these are non-linear because, let's say, in the same case, if we had uh, a conservation of phi instead of u, something like this. And so on, so some, diffusion term containing dou phi dou x, then another source term. This equation is actually linear in phi if we know u and v then. But if u or v themselves are being conserved, as is the case in this equation, Then these terms they introduce non-linearity into the equation, and that's why the correct answer would be option B, non-linear. Okay. So there will be another dodo X. Right. Okay. So we will move on to question number 2 of today's session, which is asking us to select the correct statements related to the Scarborough criterion. So there are four mathematical statements given here, and among the options there are some combinations of these statements. You have to pick out the correct combination which relates to the Scarborough criterion, which is the criterion which determines convergence of a scheme for finite volume method. So the four statements given are statement number 1, that is the ratio of summation of all neighboring coefficients over the uh, point coefficient, that should be less than 1 for all points. Statement 2 says summation over magnitude of A and B over AP should be less than 1, should be less than equal to 1 for at least 1 point. Statement 3 says summation over all A and B over AP should be less than 1 for all points. And statement 4 says summation over A and B over AP should be less than 1 for at least 1 point. So which one would it be? So if I call this particular ratio R equal to, let's say, summation over A and B over magnitude of AP, then the four statements are the four statements can be written out as follows. That is, R less than equal to 1 for all points, R less than equal to 1 for at least 1 point. And statement 3 would be this R would be exactly less than 1 for all points. And statement 4 says R should be less than 1 for at least 1 point. The options given below are option A 1 and 4, option B 2 and 3, option C 1 and 2, and option D 3 and 4. So let's have a look at the solution. The solution says option A 1 and 4, that is option 1 and option 4. So this ratio should be less than equal to 1 for all points, and on top of that it has to be less than 1 for at least 1 point. What this does is that it ensures diagonal dominance, which is necessary for smooth convergence of a solution scheme. So if these conditions are satisfied, then we will say that Scarborough criterion is satisfied, and we can rest assured that the solution scheme would ultimately converge and give us correct results. So that's why option A, 1 and 4 would be the correct answer. Okay. Alright. So we will move on to question number 3 of today's session, which is asking us that for convection diffusion equations, what is usually done to ensure that Scarborough criterion is satisfied? So, there are certain steps which are taken to ensure that Scarborough criterion is something that we do satisfy. What is that? Is it option A, upwind scheme is employed? Option B, central difference scheme is employed? Option C, Crank-Nicholson scheme is employed? Or option D, none of the above? Let's have a look at the solution. The solution is option A, upwind scheme is employed. So there are different forms of upwind schemes which we learned through the lecture series on week 11. And if we use upwind scheme, it turns out that the matrices that we develop, they are diagonal dominant and they satisfy the Scarborough criterion. And as a result, we can rest assured that uh, the solution would ultimately converge and give us correct results. So that's why in convection diffusion equations, upwind scheme is employed to ensure that we satisfy Scarborough criterion and the benefits along with it. Okay, so let's move on. We will move on to question number 4 of today's session, which is asking us that for first order upwind scheme, what is the most general way of estimating Fe phi E? Now, what is Fe phi E? It is the uh, so it is the flow term on the uh, east face of a given cell. It's the convective term, sorry, not the flow term, but the convective term. There are four options given below. So for the first order upwind scheme, what is the most general way of estimating Fe phi E? Option A is Fe phi P, option B is Fe phi E, option C is Fe phi P minus Fe phi E, and option D is the maximum of Fe0, Fen0 into phi P minus the maximum of minus Fen0 into phi E. So let's have a look at the solution. The solution is option D. So this particular function is something that is known as the max function. It takes out the maximum of whatever values you give within. So let's say in this case where I have a point P and its two neighbors east and west, and its face is denoted by small e and small w on the west side. So for the first order upwind scheme, when u is greater than 0, then this term over here, Fe phi E, this is determined as, sorry, this is determined as Fe into phi P. That is one point upwind to it. And when u is, I'll write this on the bottom half, and when u is less than 0, that is when flow is from the right side to the left side, then this same term Fe phi E, we estimate it as Fe phi E, right? So now the most general way of doing that is by expressing it like this. So if I express it like this, as we have said here, so I'll take the max of Fe comma 0 modulus into phi P minus the max of modulus of minus Fe 0 and then phi E. Now let's say when u is greater than 0, then Fe would also be greater than 0, and in that case this expression would be equal to, so in that case Fe is greater than 0, so this first term becomes Fe only and phi P, and over here in the second term f minus Fe here is negative, so it's less than 0, so the maximum of this would be 0, and 0 multiplied by phi E, that is 0 multiplied by phi E, this would be equal to Fe phi P, just like we said here. Similarly, when u is less than 0 and Fe itself is also less than 0, in that case, this expression for the first term Fe is negative, this is negative, so this would be less than 0. So the maximum over here would be 0. So it would be 0 into 5p minus. So here, since Fe itself is negative, minus Fe would be positive, and that would be greater than 0. And so minus Fe would come out, and here we have phi e, and this negative negative would cancel out, and this term is anyway 0. So finally we get Fe phi e. So this is similar to what we showed here. So by writing the equation like this, I am generalizing both cases when u is positive as well as negative. So that's why option D would be the correct way of estimating Fe phi e in a first order upwind scheme. I hope that makes things clear. Now we will move on. We will move on to question number 5 of today's session, which is asking us what is the order of accuracy of the quick scheme. Now, what is quick scheme? Quick scheme is quadratic interpolation for convective kinetics. That is the abbreviation of it is quick. So QUICK, quick. What is the order of accuracy of this scheme? Is it option A 1, option B 2, option 3, option C 3, or option D 4? What is the order of accuracy of the quick scheme? Is it 1, 2, 3, or 4? Let's have a look at the solution. The solution is option C, that is 3, third order. So in quick scheme we saw that we used Taylor series expansion to estimate phi e as phi p plus delta x into dou phi dou x at p plus delta x square over 2 factorial dou 2 phi dou x2 at p and delta x cube over 3 factorial into the third derivative of p at p and so on, plus higher order terms. Now in quick scheme, these three terms are considered and the third term onwards is neglected. So the leading order term over here is delta x cubed. I'll write this as delta x only, sorry. That's why the order of accuracy is third order, 3. Okay. Alright, so we will move on. We will move on to question number 6 of today's session, which is asking us that for u greater than 0, how is phi e represented in quick scheme? There are 4 options given below. Is it option A, 3 by 8 phi e plus 3 by 4 phi p minus 1 by 8 phi w? Or is it option B, 3 by 4 phi e plus 3 by 8 phi p minus 1 by 8 phi w? Or is it option C, 1 by 8 phi e plus 3 by 4 phi p minus 3 by 8 phi w? Or is it option D, 3 by 8 phi e plus 3 by 4 phi p minus 1 by 4 phi w? Let's have a look at the solution. The solution is option A, 3 by 8 phi e plus 3 by 4 phi p minus 1 by 8 phi w. And let us derive that. So, just like we wrote down in the previous slide, phi e can be estimated using its upwind point at phi p plus delta x into uh, dou phi dou x at p plus delta x square over 2 factorial into dou 2 phi dou x square. Now we will write this down again. So I have pi p over here, delta x, and then this is also estimated at pi p. So I'll draw the template as well. So in the template I have P over here, its face small e, then its neighboring point capital E, space W, and its neighboring point capital W. So we're trying to estimate phi E. For that we took phi P and all this. So dou phi dou x at P can be estimated as phi E minus phi W divided by 2 delta x plus this thing over here. So I have delta x square over 2 factorial into, okay, I'll write this in the line below. So the second term I have delta x square by 2 factorial multiplied by the second derivative of this. So this can be written as phi E minus 2 phi P plus phi W over delta x squared. Right? So delta x squared gets cancelled. This also gets cancelled. I can write phi E as phi P. Oh, okay, sorry. So not delta x, it's actually delta x by 2 over here. So this is also delta x is by 2. So I have another 2 here and another 4 over here. So I have phi p plus phi e minus phi w divided by 4, and here I have phi e minus 2 phi p plus phi w divided by 8. Now I will club terms together. So for phi e, it would be 1 by 4 plus 1 by 8 into phi e. For phi p, I'll have 1 up front and then minus 2 by 8. So that can be written as minus 1 by 4. And for phi w, I'll have minus 1 by 4 from this second term and plus 1 by 8 from the second term, from the third term, sorry. So finally, I can write this down as, so 1/4 plus 1/8 is basically 3/8 into phi e plus 1 minus 1/4 is 3/4 of phi p, and sorry, not plus. So this would be minus 1 by 8 of phi w. So this corresponds to the first option. Option A, that is 3 by 8 phi e plus 3 by 4 phi p minus 1 by 8 phi w. Right? Okay. So moving on, we will move on to question number 7 of today's session, which is asking us which terms are absorbed into the flux term J vector while integrating the governing equations. So we integrate the governing equations, which are nothing but the conservation equations of different physical quantities. So in that case, we define a flux term while integrating over a small control volume in finite volume method. So while doing that, there are some terms which get absorbed into the flux term. Which are those terms? There are several combinations given in the options below. So there is option A, transient term plus convection term. Option B, convection term plus diffusion term. Option C, diffusion term and source term. And option D, convection term and source term. So if I write down the general form is this. I'm writing in 2D vector form. So this would be grad of rho u phi. Then this side we will have grad of lambda grad phi, and then there will be a source term, source of phi. So this is the transient term. This is the convection term. Over here we have the diffusion term, and this is the source term. So while integrating, which of these terms gets absorbed into the flux term? Let's have a look at the solution. The solution is option B, convection term and diffusion term. So what basically happens is if I go back, so we move this diffusion term to the left hand side and we get something like grad of rho u phi minus uh, capital gamma grad phi, and then we say that this is nothing but the flux term. So these are the two terms, convection term and the diffusion term, which gets absorbed into the flux term. Right? Okay. So we will move on. We will move on to question number 8 of today's session, which is asking us which is the correct expression for Peclet number. Is it option A, Peclet number equal to rho u delta x over gamma? Option B, rho delta x over u gamma? Option C, rho u by gamma delta x? Or is it option D, u delta x over rho gamma? So Peclet number, it was defined as the ratio of convective flux over diffusive flux. Let's have a look at the correct solution. There is option A, that is Peclet number equal to rho u delta x over gamma. So what happens is Peclet number is nothing but the ratio of the convective flux over the diffusive flux. These are the coefficients, the convective coefficient and the diffusive coefficient. And we know that the convective coefficient is equal to rho u delta x over a, sorry, not delta x, rho u over a, and AE rather into phi as well, PE. And this thing over here, the diffusive quantity, this is equal to gamma into phi E over delta X into AE. Now, if I take a ratio of these two over here, I'll just simply plug in these two values over here. So I have this multiplied by gamma PE into AE into delta X. AE gets cancelled, phi E gets cancelled. What remains is rho U delta X over gamma. That is the first option, option A. Clear? So let's move on. We will move on to question number 9 of today's session, which is asking us that which is the requirement for cell Peclet number so that Scarborough criterion is satisfied. Is it Peclet number equal to 2? Is it option B Peclet number less than 2? Is it option C Peclet number greater than 2? Or is it option D none of the above? Read the question carefully and try to figure out the correct solution. Which is the requirement for cell Peclet number so that Scarborough criterion is satisfied? Is it option A Peclet number equal to 2? Option B Peclet number less than 2? Option C Peclet number greater than 2? Or is it option D none of the above? So let's have a look at the solution. The solution is Yeah, the solution is option B. Peclet number should be less than 2. So basically, what happens is in finite volume method, while we're trying to find out the coefficients. So in that case, the coefficient for the east face, that becomes, you know, something like, the east cell becomes something like this. So I have dE minus Fe by 2. Now, in order that Scarborough criterion is satisfied, AE cannot be negative. So DE should be greater than Fe by 2, and if I try to write it down in a different way, Fe by DE should be less than 2. And we have defined that this Fe by dE is nothing but the Peclet number. So the Peclet number should be less than 2. So that's why the cell Peclet number is an important parameter, and we have to make sure that at all points this cell Peclet number is maintained at less than 2. Otherwise, the Scarborough criterion won't be satisfied, and we won't have diagonal dominance, and ultimately our solution might diverge. Okay. Now we come to the last question of today's session, which is asking us that at convergence, what is the value of the sum of the convective coefficients? So is it option A, summation over FF should be equal to 1? Option B, summation over FF should be less than 1? Option C, summation over FF should be greater than 1, or that summation over FF should be exactly equal to 0. So let's have a look at the solution. The solution is option D, summation over FF should be equal to 0. So basically these FFs are nothing but the FE, FN, FS, and FW, and so on. So these are nothing but the flow through the cells. So basically Fe means the flow out of this cell, Fn means the flow out of this cell, Fw is this and Fs is this. So summation of Ff is nothing but essentially Fe plus Fw plus Fn plus Fs, and these are nothing but the fluid flow fluxes across the faces of the control volume, and at convergence the continuity equation must be satisfied, and in order to do that this sum should be equal to 0. So that's why at convergence the summation of Ff becomes identically 0. That's why option D would be the correct answer. I hope that things are clear. That's it for this week. See you again next week. Until then, thank you.